So thank you everyone for joining today's session. Before we begin, I'll pretty much give you a quick introduction of myself. So my name is Aleksandar Sofranic. I joined Cisco TAC in 2016 in the routing protocols team. There I was pretty much supporting all the routing protocols, BGP, MPLS, L3 VPNs, L2 VPNs. We were also supporting a lot of data center technologies such as OTV, Lisp, and VXLAN, which was pretty cool, and a lot of multicast cases also. So when I got my CCIE, I decided to move into the service provider space, where I'm currently working in Cisco TAC in Sydney, in the XR team. So there I'm pretty much supporting all the XR products, NCSs, ASR9Ks, and the CRS devices. It's pretty good. Currently in the XR team, we're getting a lot of segment routing cases and EVPN cases, so it's getting pretty interesting. Mandatory side, so we have the WebEx Teams. Join the discussion. It's going to be open for around 2 weeks, so if you have any questions, just punt those questions there, and I'll get back to you. So what do we expect from today's session? We're going over multicast fundamentals. We're going to be focusing on PIM and IPv4. We're going to be going over IGMP. We're going to be going over the RPF check, and we're going to be going over so PIM, RPF check, and IGMP. Right? Once we understand those fundamentals, we're going to be leveraging that on how we build an ASM tree and how we build an SSM tree. Now, if you're already familiar with multicast, SSM is much more simpler than ASM, and we see a lot of tickets with ASM in TAC, so we're going to be focusing a bit more on ASM. Once we pretty much get those fundamentals out of the way, we're going to be diving into troubleshooting multicast. So we're going to go over the troubleshooting methodology of multicast. How do you really approach troubleshooting multicast? Now, throughout the years working in TAC, I found that if you have an issue with multicast, it's quite hard to understand where that issue is. If it's not a migration and you change the router, right? If you haven't changed the router and multicast stops, well, it's kind of hard to understand where the issue is. So we're going to be focusing on the methodology of troubleshooting. I pretty much made up 6 troubleshooting tickets, and in those troubleshooting tickets, I'll be focusing on common deployment issues, which I've seen throughout the years. And also, we're going to be highlighting the concepts we're going to be going over in the fundamentals. So session goals and questions. Regarding session goals, we want to be up and running with multicast. We want to really understand those fundamentals. So if you have any questions regarding those fundamentals, definitely put your hand up, right? If you have a question regarding the slide, most likely someone else also has a question. So don't hesitate to put your hand up and pretty much shoot those questions. Now, if the question is particularly off topic or it may be a longer question, we only have 90 minutes for today's presentation, so let's take those questions after the presentation. Session goals, well, if you're deploying multicast, can we get a show of hands who's maybe deploying multicast in the next 6 months? Okay, and who's maintaining a multicast network? Okay, cool. So if you're deploying it, right, you don't want to be on the spot, all eyes are on you, it just doesn't work, right? You deploy it, doesn't work, you want to know how to troubleshoot that. If you're maintaining it, well, you want to know what to do when you get that call at 2 o'clock in the morning. You want to start troubleshooting and make some progress, right? So there's going to be added value for both of you. So let's start with pretty much multicast fundamentals. So we have 2 diagrams here. The top diagram is pretty much, we're deploying, it's an example of deploying unicast for, let's say, a multicast application. So what issues could you have? And let's say you're saying multicast is too complex, I want to just deploy unicast, right? We see that the first issue you may observe is that you may have congestion on that first link there. And that's because you have a unique source and destination, and that's a flow, right? So for every destination you're going to, that's a unique flow, and you have to push out packets for this. So first of all, you may have congestion there, but not only that, but the server also may not be able to push that amount of traffic because it doesn't really scale well, right? If you have maybe 200 receivers, it may work. You want to scale to 1,000, well, you're not going to be able to push a lot of traffic off that link. Also, it could be the case that you have some WAN deployment, right? Maybe multicast over DMVPN. You don't want to be pushing so much unicast traffic over those links. So we came up with multicast. What does multicast do? We see that we have a source, and that source is going to pretty much push one packet out, right? Or it's one flow. And when he pushes that out, we see that those routers, they're going to actually do some magic there. They're going to replicate those packets downstream towards receivers, right? So it scales really, really well. Use cases, well, there's lots of use cases, right? Music on hold, live video distribution. Can we get a show of hands? Is anyone anyone have VXLAN in their network? Awesome. So you may be using ingress replication or multicast. Throughout the years, I've seen that a lot of people are actually running multicast. So you need to know multicast if you have VXLAN, right? So there's lots of use cases for multicast. Now, considerations, right? With every technology, you do have some considerations. Multicast does leverage UDP. So first of all, it's best effort delivery. You send out a packet. You don't really know if that packet's being received by the receivers, right? What about congestion avoidance? Well, it's not TCP. So you don't have TCP slow start, TCP windowing, right? You just pump out those that gig stream, whatever, and you can't feel the network for packet loss and duplicates. Now, we saw in the previous slide that we actually are doing some kind of replication, right? And that may lead to duplication. Now, if you have more than a second of duplication, it might be wise to maybe even open up a attack case and see if that is expected. However, I've seen throughout the years that some companies actually leverage duplication as a form of redundancy also. So they actually want to have duplicate packets, so it's pretty much a redundancy mechanism. So if you look at the IPv4 header, it's pretty much the same for unicast and multicast. Not much difference except for the destination. The destination is going to be a class D. The source, class A, B, or C. Do not put the source as a class D. That's not going to work, right? So it's really important that those servers or sources that you're configuring, they have to be a class A, B, or C, right? Multicast addressing, just some pointers here. So first of all, multicast routes actually are stored in a different routing table. If you do show IP route or you're familiar with routing, you're never going to see a multicast route in the unicast routing table. It's always going to be in the multicast routing table. So that's something to take into consideration. Really, really important point here is that multicast states are initiated by receivers, meaning that if you have a receiver, he's going to signal towards the network through some protocol, hey, I want to receive multicast traffic, and then that router receives the state and he builds the tree for them, right? If you don't have receivers, you may not even have a tree built in multicast. So that's really, really important. What about sources? They don't really do much except for send traffic. You don't need to have any signaling protocol. You just send on the wire, and that's it, right? Those first hop routers, those routers connected to those sources, they have to do the heavy lifting regarding multicast. Source reachability. So multicast routing protocols, we're going to be talking about PIM. PIM builds and maintains the tree. We're all familiar with building the tree. Maintaining the tree is also something that's some people are not familiar with, so we actually maintain the tree. We're actually going to see that we actually send PIM joins or join prunes every minute to refresh that state. And we're going to have a look at the PIM states there. Source reachability is derived from the unicast routing table. Very important point. Now imagine that you have a source which is sending and you have a receiver. Think about it that if you want to ping from the receiver towards the source, how do you get to the source? Unicast routing table, right? So it's really important that you have that source in the unicast routing table because otherwise you may not be able to build a multicast tree. We do have some multicast addresses here. So if you're familiar with networking, they may be fond to you, I guess, OSPF, PIM, IGMP, AGRP. They also use the reserved link local addresses. It has TTL of 1. You don't expect to route those packets off the subnet. And then we have the reserved addresses, pretty much similar, just they have a TTL higher than 1. What you want to get out of this slide is that you don't want to use those ranges for your multicast streams, right? Don't use those addressing spaces. The addressing spaces you want to use, administratively scoped addressing space, 239/8. Oh, sorry, I thought you had a question there. 239/8 is pretty much like RFC 1918, private addressing space, and then we have SSM, which was built for the internet, pretty much 232/8. Layer 2 multicast addressing. Well, if you have a layer 3 destination, which is multicast, you're going to have a destination MAC, which is multicast also. We have the prefix of 01005E. It's pretty much a prefix, which if you're doing any debugging or packet captures, if you see that particular prefix there, you know it's a multicast destination. Also, the lower 23 bits of the IP address will be mapped to the lower 23 bits of the Ethernet header. So that's just a pointer. Okay, so let's have a look at the multicast route. So if you're not familiar with multicast, this is pretty mind-boggling, this route here, right? We have two very important IP addresses, this one and this one here. So on all the routers, you're actually going to know who is the source who's sending multicast. That's the red field. That's going to be the source of the server who's sending multicast. And then we know that that server is sending to that group. That's pretty cool. You're going to have this on all the routers, right? Now, we have a question. How does the host signal it is interested in a group? So let's say I'm a set-top box or I'm a PC, and I want to say, hey, I want to listen to a particular multicast group. How do we signal this? IGMP. Who was that? Awesome. IGMP. Right? We use IGMP for set-top boxes or hosts, and they pretty much leverage this protocol. Now, we have three versions of this. Version 1, version 2, version 3. Version 1 is very old. Version 2 is very old. And version 3 is very old. So all of them are very old. So if you're not leveraging IGMP version 3 in your network, you better be asking yourself why you're not leveraging this. The vendors should support this already, so make sure you're leveraging this. And we can have a look at the RFCs, right? RFC 2236, RFC 3376. That's like, we're up to RFC 8K now, so it's really old. But the point here is that we actually leverage this protocol for signaling from hosts. And we're going to have a look at this now. So we have this particular network here, and we have host 2. And host 2 may be a set-top box, a PC, whatever. And he wants to listen to the group 239.1.2.21. He generates an IGMP v3 membership report. We're going to be discussing IGMP v3. He sends out an IGMP v3 membership report, and he says, OK, I want to listen to this particular group. Right? He sends it out. The destination of the packet is going to be the link local address of 224.0.0.22. He sends it on the shared segment, and he has the exclude field empty, meaning that he doesn't want to exclude any sources. He just wants to receive multicast for this particular group. So he's going to pretty much pull all the sources who are sending. One more point here is that the destination actually is solicited. So if you're running IGMP v3 on your interface, that interface is going to be solicited to listen to IGMP v3 membership requests, and only the routers will be receiving this. Now, when the router receives this IGMP v3 membership report, the router creates IGMP state. And we see there we have, if we do show IP IGMP groups for that particular group, we see that we know that there is a receiver on the shared segment who wants to listen to multicast, and that's the group he wants to listen to. And we see the source list is empty. He doesn't care about what sources are sending to this particular multicast group. He wants to receive everything. OK, what if we want to leverage including a source, right? Now, we're going to do this with the include field. We pretty much specify an IP address there, which is the source, and we send an IGMP v3 membership report out. The router now understands that there is a receiver out there that wants to listen to that group from that source. And remember, IGMP v3 gives you this capability. IGMP v2 does not. It can only specify I want to listen to a particular multicast group, but not the source. IGMP v3, you can leverage, hey, I want to listen to that source sending to that group. Very important. OK, maintaining state. So a router will send a membership query out, and all hosts will receive this and send out an updated membership report specifying what the most up-to-date groups are that they're listening to. So that's how we maintain the state. A few pointers here. So multicast forwarding. Forwarding is connection-oriented, meaning that, as we saw, the receiver signals to the router he wants to listen to multicast. Also, that router is going to signal to other routers towards the sources they want to listen to multicast. So it's really connection-oriented. First, we build that multicast tree, then we push multicast traffic down. Now, how do we leverage this join process in layer 3? We actually use pim join prune packets. Now, per RFC, it's a pim join prune message. You can either say it's a pim join prune packet, which has a joinator or a prune or a join prune, or you can just say it's a pim join. So we're going to leverage both terminology here. Convergence is derived from the unicast routing. Convergence is dependent on the unicast routing table. We've had tons of cases where we have a ticket open, multicast is not working, and the root cause is that unicast was not working. Make sure that your unicast routing table is fine. You didn't have any convergent events. You didn't have any traffic drops. Yeah, go ahead.
So it forwards out all interfaces the prune join request because it doesn't know where the source is, right?
PIM, so PIM,
It hasn't been given a source, that is.
yes, so we're going to be going into that. That's ASM. So when we send the PIM join prune packet out, we're going to specify, okay, we want to listen to that source, to that group, or if it's ASM, we leverage the rendezvous point. We'll get to that question, that awesome question. So make sure your unicast routing table is fine. Check that. How do you route to the source? Did you have any convergence events? It's easy to check, right? In OSPF, you can see when the update, or if the route was updated. If it was updated and it matches the time when you had a blip in your stream, that may be the root cause of your issue. Okay, we have two questions here. How does the last hop router signal towards the network? We want to listen to a multicast group. Now, last hop router, this is terminology we need to go over. Last hop router is always going to be connected towards a receiver. First hop router is always connected towards a source. So how does that last hop router send towards the network that, hey, I want to listen to a particular multicast stream? PIM joins, perfect. Okay, what about the next question? How does the last hop router know where to send those joins? How does E know to send to B? Routing table, perfect. And we leverage the RPF check. So now let's touch upon the RPF check. So an RPF check usually uses the unicast rib, and we'll have a look at the troubleshooting section. And it determines how do we get to that source. If the source is 2 hops away going towards B and C, we go towards B and C and we say, hey, pull that multicast stream down. Very simple. Okay, we have, with the RPF check, we actually determine what's the interface and what's the PIM neighbor we want to go to. Very important. Now, incoming and outgoing interfaces. Yep.
Just a quick question. What about in the case where the WAN network is managed by a telco provider and we have no visibility to that? We only have the 2 endpoint devices.
So, yeah, that's a really good question. So to repeat the question, what if you have some service provider in between and you're an enterprise, right? Well, then the service provider needs to worry about their PIM states, and you need to worry about your PIM states, right? If you see that you have correct state on your network, right, and you send a PIM join towards the service provider, and you have valid state, and you're not receiving multicast traffic, I would call up the service provider and ask them, hey, what's going on? And we're going to actually have a look at how you can troubleshoot data plane in that scenario, but awesome question. So incoming interface list, it's very simple. Incoming and outgoing interface list. Incoming interface list is going to be towards the root of the tree. Now we're discussing pretty much S, G here. So we have S is 2.2.2, that's the source, and G is the group. So incoming interface is always going to be towards the root of the tree. Root, in this case, is 2.2.2.2, right? The root is the source. We want to build the tree towards the source, and the source pushes multicast traffic down. Now, once I've calculated my incoming interface list, once I've calculated my, you don't hear me. Better. So once I've calculated my incoming interface list, my outgoing interface list is towards receivers. So I expect to receive multicast traffic coming in my incoming interface list, and outgoing is towards receivers. Now, if you're directly connected towards a receiver, that's populated by IGMP. You may have routers which signaled they want to listen to multicast traffic, and then you say, okay, I'm going to populate my outgoing interface list towards that router. So incoming and outgoing interface list. Now, 2 more things we want to discuss here. This RPF neighbor. This is very important. This is your neighbor where you want to send your PIM join prune packets. What we have there, it's actually a multicast packet. We'll see that in the next slide. OIL entries, also very important. OIL entries are refreshed. Now, when we said that PIM builds and maintains state, if I don't maintain, there's a router, let's say there's a router behind one of the outgoing interface lists, and that router stops sending me PIM join prune packets. He reloads and doesn't come up again. That outgoing interface list is going to be pruned after 3 minutes if I don't receive a PIM join prune, which is going to refresh this state. Okay, let's have a look at the RPF calculation. So, E wants to get to the root of the tree, right? He receives an IGMP v3 membership report, and we see that we want to get to 10.1.1.1, right? What does E do? He checks his unicast routing table. In his unicast routing table, we have a /24, interface is Ethernet 0,0, and we have a next hop of 1.1.1.1, which is B. E creates mroute state. He populates his outgoing interface list and incoming interface list, and sends a PIM join prune or a PIM join towards B. B now does the same thing. He checks, okay, how do I route towards the source? I'm going to now populate my incoming interface list, outgoing interface list towards E, and send a PIM join towards A. And voila, multicast flows down. Pretty simple, right? Now, when you think of multicast, you're saying, oh, multicast is complex. That's all because of ASM, right? This is SSM. SSM is beautiful. So, if you get another receiver, well, you just join the source of the tree, which is the source, right? Okay, so what if we have ECMP in our network? What happens then? Can we send, so router 1 receives an IGMP V3 or V2 membership report, and he now, well, V3 in this case, and he wants to go towards the source, right? Now, if he has ECMP, if he sends a PIM join towards D and towards E, is that an issue? Seems like it's going to be duplication, because then D and E will go towards B and C towards A, and then we get pretty much duplication of the flow. So we can't use both. Now, what's the tiebreaker? Does anyone know? Sorry? Close. Getting better. Highest IP address. In RIB. We check RIB. We have ECMP, right? OSPF example. We know this via OSPF. Those two routes, we have ECMP and OSPF. And we understand, okay, to get to the source, we have a next hop of 1.1.1 via D and a next hop of 1.1.2.1. We just check the highest IP address. Who has the highest IP address in RIB? That's where we send it. Now, if you have ECMP in your network, maybe you want to leverage ECMP, right? So we do have a solution for that. It's called Multicast Multipath. It doesn't do ECMP. It does load splitting. It's different. It pretty much does a hash, and it can say, okay, if you have this source sending to multiple groups, maybe for group A, I'll use D. Maybe for group B, I'll use E in this case, right? So, okay, regarding PIM, just a quick overview. So, PIM, protocol independent multicast, right? Why is it independent? Because we don't really care how we discover the topology. If you're running OSPF, if you're running EIGRP, if you're running BGP, we pull that information. As we said, the incoming interface list is populated via RIB. We pull it from RIB, and we say, okay, I'm using EIGRP, I'm using OSPF, it's unicast RIB. I'm going towards the source. Now, there's three main classifications of PIM: ASM, SSM, and BIDIR. Can I get a show of hands who's running BIDIR in the network? Perfect, so no one. We're not going over BIDIR. We're going over ASM. Who's running ASM in their network? Okay, and SSM? A few people. Oh, that's perfect. Okay, so yeah. We're going to be going over ASM and SSM. Before we go into pretty much building trees, we need to build a neighborship, right? Just like in OSPF, if I want to send a link state update towards one of the routers, the router needs to be configured with OSPF, or he'll pretty much drop the packet. He doesn't really care about OSPF if he's not configured for it. Same with PIM, right? We want to have PIM neighbors. Now we send out pretty much hello packets every 30 seconds, and this is how we build a PIM neighborship. And one really important point here is that we see there an existence of an RPF interface without an RPF neighbor is no good. And we're going to see that in the troubleshooting section. Okay, DR. This is, I can't emphasize how important this is, and we're going to see it in the troubleshooting section. So know who the DR is. The DR has two really important responsibilities. It registers sources to rendezvous points, new sources. If you're a first hop router, it registers those sources. If you're a last hop router, it's going to build the tree towards either the rendezvous point or towards the source if it's SSM. Right? Really important. How do we elect a DR? Highest IP address. You can manipulate this with DR priority. If you're running DMVPN with multicast, then spokes can be configured with 0. This is going to be don't elect me as the DR. I'm not even participating in an election. 1 is default, higher the better, and it's preemptive. Important points there. Okay, PIM join prune packets. Now, how does that actually look like? If we have a look, C wants to send the PIM join prune packet towards A. The source is going to be himself, unicast. the destination is 224.0.0.13, all PIM routers. That's the destination. Inside the IP packet, we're going to have a PIM header with the group, and we want to join a particular source. So how about we spice it up a bit now? What if we have this scenario? C actually wants to send a join towards B, but there's actually A also on the shared segment. And what am I emphasizing here? The destination of the IP packet is all PIM routers. So how do we know who's going to interpret this PIM join message? And this is very important that you brought that up. DR is important when you're a last hop router and a first hop router. Very important. Through the transit network, not too important. So, how do we know? We send it on the shared segment. A receives this PIM join and B receives it. Well, we look at the IP head, we look at the packet capture, and we actually see that we have upstream neighbor field. That upstream neighbor is our RPF check towards the source, an example. So when, let's go back. So when A receives this, an example, A receives this PIM join, the destination is going to be multicast, but inside the PIM header, I'm saying, hey, B, interpret this. A says, oh, that's not me, right? I don't care. B says, oh, that's me, so I have to work now, right? So that's how it is. Okay, SSM. Let's have a look. So we leverage S, Gs. We don't leverage star, Gs. We'll have a look at what star, Gs are. Hosts are responsible of learning source information with IGMP v3. So if I'm a set-top box, I need to understand, okay, I flick to Cartoon Network or Channel 7, Channel 10, right? I need to know, okay, Channel 10 is this server to this source, right? I need to know that information. No SPT switchover. We don't have much complexity there, as we saw. No shared tree and no RPs. What a beautiful protocol. So how does it work? We have a receiver. He may query an out-of-band management server specifying, okay, give me the up-to-date sources and groups mapping. The receiver receives this, and now he sends an IGMP v3 membership report towards the last hop router. This last hop router receives this and says, okay, I want to build the tree towards the source, right? So he checks his unicast routing table, populates his incoming and outgoing interface list, sends a PIM join towards the source, gets to the first hop router pushes traffic down. Pretty simple. Okay, SSM considerations. IGMP v3, you need to leverage this in your network, right? Because it's dependent on IGMP v3. It's supported from Microsoft XP, from Apple products, and quite a lot of vendors support it. Now, if your vendors don't support IGMP v3, ask them why don't they support it. It's going to make your life much easier. Now, if you can't leverage IGMP v3, you're going to have to leverage IGMP v2. So there are some transition mechanisms or workarounds. First is to configure static mapping. If you're a last hop router, you can say, okay, if I receive an IGMP v2 membership report, I can say, okay, that group which you sent me, that maps to this server, and I send an S-G join towards the source. Now that may be administrative overhead, right? If you have a lot of last hop routers, you don't want to be continuously updating who the sources and group mappings are. You can also leverage DNS. DNS, you can pretty much query a DNS server and specify, okay, I've got this group, who is the source that maps to this group, and then we can send an S-G join upstream. Okay, multicast distribution trees. We have the shortest path or the source tree. This is what we've been discussing all along. We go directly towards the source, right? Now, what about shared tree? This is what you're going to leverage in ASM and BIDIR. A shared tree has new terminology here. It's the rendezvous point, the meeting place in the network, right? Now, this meeting place means that, let's take just a vague example. A receiver sends, I want to listen to the group 239.1.1.1, but I don't know who the sources are. So where do I go? I go to the meeting place where sources and receivers fall in love, right? We go to the rendezvous point, and the rendezvous point now understands that, okay, all the sources are going to be pushing multicast traffic down towards the rendezvous point. All receivers are going to join the rendezvous point, and we pretty much push multicast traffic down. Now, with just shared trees and BIDIR leverages, leverages this, we only have star comma Gs. We only have star comma Gs here. All routers need to understand who the RP is. And you can think of this as a dating service, right? You want to meet, I'm a receiver and I want to fall in love with a source. I go to the meeting place and maybe a cafe. We go there, I meet the sources, and I pull the traffic down. That's how it works. Okay, ASM. So this is... Yeah, so there are multiple ways of pretty much propagating RP information. You can leverage BSR, you can leverage auto RP, or static RP mapping. So those are pretty much the options. I prefer static RP mapping because in the case of troubleshooting BSR or auto RP, it may be complex. So. Okay, ASM. I'm breaking down ASM into a few pretty much steps. ASM leverages the source tree. We go directly towards the source, but we also go directly towards a rendezvous point. We're going to see that. I've broken it down into a few steps. First, we do PIM SM registering. A multicast source starts sending. We need to register this to the rendezvous point. We need to join the shared tree. So I'm a receiver. I say, hey, I want to listen to group 239.1.1.1. I don't know who the sources are. I go to the meeting place in the network. Once I receive a multicast packet, I go to the S, G. I go to the source directly because I know who the sources are now. Right? If the last operator receives a packet, he knows where to go. Right? And then we want to prune the rendezvous point. So we're going to go into detail on each of these steps. Okay, source registration. How this works is that when a source starts sending multicast traffic, F here is the first operator. He receives this multicast traffic, and he actually encapsulates this multicast traffic into unicast and sends it towards the rendezvous point in a PIM register message. It's unicast. Rendezvous point receives this. He decapsulates this data packet. He checks the IP header and says, okay, this is the source, this is the group. Let's create state. He creates state. He knows now that there is this source and this group on the network. Right? If we have any questions, don't hesitate to ask. RP, when he receives this, depending on the state on the RP, he sends a register stop saying, don't send me those register messages anymore. I've decapsulated that packet. I know who the S, G is. And that's it. Stop sending those multicast packets. Right? It could be a burden on the CPU if you're constantly encapping those data MCAST packets into unicast. And we do maintain this state by null registers. So the first operator is actually going to, after some time, he's going to send a null register. A dummy is going to be a PIM packet with a dummy IPv4 header there stating, hey, this source is still sending, update the state on the rendezvous point. Okay, how do we join the shared tree? We receive an IGMP v2 membership report on A. Yep?
Sorry, just back on for, so that will scale to multiple sources as well. If there's more than one source for that multicast group,
yeah,
it will just kind of repeat the process.
Registering process or maintaining?
What if a new source is added after that process happens?
Same.
Yeah.
If it's a new source, it's a new S, G. Maybe the group is the same, but the source is different. So we need to register this to the rendezvous because it's a new source. We receive an IGMP v2 membership report on A. A now creates IGMP state. He knows there's a receiver who wants to listen to multicast. And what does he do? He doesn't know who the sources are, right? Because it's a v2 IGMP membership report. He's just specified, I want to listen to the group 239.1.1.1. I don't know who the sources are. So I go to the meeting place in the network. I generate a star, G. Star means join any source to this particular group. And the root of that tree is going to be the rendezvous point. So I go towards the rendezvous point. I check, it's just like checking unicast routing table. Okay, how do I route to the rendezvous point? That's how we populate the incoming interface. I go towards B. B does the same thing. He creates an incoming interface list. Incoming towards the rendezvous point. Outgoing towards A, because A wants to listen to multicast traffic. And we go to B sends the star comma G join towards the rendezvous point. Now, what does the rendezvous point do? That really depends on the state. If the rendezvous point knows about sources sending to this group, he's going to join the S comma G. He's going to join the source with S comma Gs, pull the multicast traffic down towards him, and push it towards receivers. If he doesn't have any sources which have registered for that multicast group, well, he does nothing, right? He can't join any sources that he doesn't know. Okay, once we've joined the shared tree, and now we receive multicast packets down, right? So the rendezvous point, he joined the source, he pulled the multicast traffic down, B's received it from the shared tree, A receives this multicast packet, and now he's smart enough to say, okay, I understand who the source is in the network. I know who the source is in the network. The packet, the data packet's being received. I push it to the receiver. What does he do? He creates S comma G state. With this S comma G state, now he does an RPF check towards the source. Not the rendezvous point. Star comma G is already built. Now he has S comma G, so he wants to join the source tree. And it makes sense. You want to go directly towards the source. Going towards a rendezvous point may be suboptimal, right? If your rendezvous point is 5 routers away, but your source is 2 routers away, why would you go over the rendezvous point? You want to go towards the source and build a tree and push that, receive that multicast traffic down natively. We send an S comma G join towards B. B receives this and he checks, okay, how do I get to the source now? He sends an S comma G towards the source. Any questions? Okay, now we're receiving multicast traffic, the same flow from the rendezvous point and from the source, right? We see it there. Yellow line is from the source, data packet. Blue packet is from the rendezvous point. It's the same flow. Now B says, well, I don't need that, right? I don't want two flows here. I want one, right? So what's less optimal? It's the rendezvous point. I don't want to receive multicast traffic from the rendezvous point if I'm receiving it directly from the source. And we have the T flag there stating that we've actually received the data packet from the S comma G. So how do we fix this? Right? We don't want to receive those duplicate packets. What we do is that we actually send an S comma G with the RP bit set. It's a big word, and it's not complex. So it's pretty simple. What B does is he sends a prune towards the rendezvous point saying, hey, don't send me that S comma G traffic anymore. I don't want to receive that. I'm already receiving it natively. So he sends a PIM packet. He includes the S. He includes the G. And there's a flag there, which is the RP bit, stating my RPF interfaces are going towards the rendezvous point. That's it. Rendezvous point receives this, and he says, OK, I'm not going to send traffic for that S comma G anymore towards those receivers. So then we have this scenario, right? We're just receiving traffic from the source. Do you have any questions on how we build the ASM tree? We can see it's quite complex, right? When you think about SSM, you go directly towards the source and you don't need to think about anything, right? Here, there's meeting places in there, there's pruning, there's a rendezvous point. It's just, a formula for issues, right? In TAC, most of the cases that we have, it's going to be ASM, right? So, okay, troubleshooting multicast. There are 3 questions you want to always ask yourself when troubleshooting multicast. Who is the rendezvous point with ASM? Who is the rendezvous point? Do you have RP mapping? Where is the route? How do you know the route? Where's the IP address, right? You do show IP route or show RPF to the source. You need to know how do you get to the source or to the root of the tree, RP or source. And then what's the neighbor? As we said, it's not enough to have a PIM an interface towards that RPF neighbor or towards that source. You need to have an RPF neighbor. You need to have PIM neighborships between those devices. Now, these questions pretty much brought to you by Fish Fishburne, a solution architect in Cisco. She's really good. She has awesome presentations on troubleshooting multicast, so if you have time, go over them. Also, there's an awesome book by Bo Williams. Pretty much, he's unbelievable. He has a really good book, Developing IP Multicast, so go over that also. He's going to give you all the information. Okay, 2 questions here. Does anyone know the answer to the first one? And I have some prizes here, actually. I have some chocolates, so added motivation, right? Besides all the free food you're getting outside.
You just stole it from there.
So does anyone know the answer to the first question? With ASM, may we see S, G state if the source is not sending? The logic is very simple. You have a receiver. The receiver is sending an IGMP v2 membership report. He's saying, hey, I want to listen to this group 2391.1.1. The router receives this. Router says, okay, I know that there's a receiver who wants to listen to the group 2391.1.1, but I don't know the source. Where do I go? To the rendezvous point. I jump to the rendezvous point, and the rendezvous point says, well, no one registered. There's no source which is sending. You need to send multicast to register, so rendezvous point doesn't know either. So the answer is no. That's one bag of chocolates for me. Yes. Let's go with the second question now.
What if it was sending and it stopped and hasn't been pruned?
What if it was sending a...
What if it was sending, but
Yes.
it's since stopped and hasn't been pruned out of the tables?
then we would have S, G state. Yep. So that may be a corner case actually, because it may take some time to prune it, right? So you got a good point there.
Half a bag of chocolate.
I was really looking forward to this bag of chocolates, you know. All right, second question. Hopefully this bag's for me. So with SSM, what did we say? What's really important with SSM? Receivers need to know what? The source. So may we have S, G state in the network if the source is not sending? Yes. Oh, well, I don't have that much chocolates for all of you, so. Who said it first? Who's really eager for a bag of chocolates? Me. Oh, yes. All right. So the answer is yes. The logic is simple, right? You receive an IGMP v3 membership report. You already have SG there. The router receives this, and he says, all right, I already have S, G. I build the tree towards the root, right? Now what we've seen is in TAC is that sometimes we have cases where, hey, I've got all the states in the network. Everyone has S, G. I'm not receiving any multicast traffic. Why is that? Because the source is not sending. Make sure with SSM, the source is sending. Go to that first hop router and run show IPM route count and see those packets coming in. Right? If they're not coming in, you have S, G everywhere, but bad luck. The source is not sending, so you're not going to push all that traffic out. Okay, awesome. Okay, question here. Do we expect star, G for SSM? No, I think somewhere there. All right, here you go. Bag of chocolates for you. All right, so good. With iOS, we actually have IPPM SSM default. This is going to configure the 232/8 group as SSM. You need to configure this with iOS. NXOS, I believe it's already like default configuration, and XR also. So don't need to worry about this on those platforms. Okay, I've included these commands here. iOS, NXOS, iOS XR. Don't we love when we have an iOS device and we jump on XR and then we're like, oh, what's the command? And then we go into NXOS and we're like, oh, what's the command? So yeah, I pretty much included that output there, so you can copy-paste that right into your notes, and then when you wake up at 2 o'clock in the morning, you're like, oh, okay, at least I have the commands, right? Just run them. So there you go. Okay, troubleshooting ticket 1. I'm not going to make this easy because if you wake up at 2 o'clock in the morning, it's not going to be easy, right? So we have last hop router, we have the rendezvous point, and we have the first hop router. These are 3 checkpoints you want to have in the network if you don't know at all what's going on, right? Make sure you have show IP mroute for the group and hopefully the source, which is having issues. In this troubleshooting ticket, we're going to have pretty much always the same source, always the same group. This is the output we have there. Okay, we have clouds. Clouds are transit devices, right? You're not going to just have 3 devices in your network. If you do, well, you're a lucky person. Most of the time, you're going to have 100, 20, 30, 500, 1,000, right? So those are the clouds. Now, this troubleshooting ticket, it's pretty much a migration for a hospital. 30-minute migration. The last hop router was replaced. IP addresses were changed. All other configuration is the same. They push that new router in. They replace it. And they say, I only have star, G state. What's going on? So this already hints us, okay, where is the issue, right? We already know something was changed, so we may focus on the last hop router. Now, does anyone see anything weird in this output? Oh, we got some experts here. Good. So you're going to get me broke here. Management is going to get angry at me. I'm giving so much chocolates away. All right, so rendezvous point. Perfect. Okay, what about this? Just a second. All right. Okay. What about, incoming interface list? What's wrong here? Yeah, no. Well, is that expected because we don't have an RP? We don't even know where to go. Okay, good. We have some smart people in the room. Okay, good. So why is the rendezvous point all zeros? Well, it's statically configured. So, we configure the rendezvous point. It looks like when the customer was pasting configuration, there was a parser error. So now we go into Notepad++. We compare those two running configurations. Everything's the same except IP addresses, which is expected. Okay. So we configure it. We have an RP. And then now we have a rendezvous point. We have incoming interface list. That looks good. What about outgoing interface list? Why is that now? Perfect. That's the logic. Then we check, we check show IP IGMP groups, and no, we have an IGMP v2 membership report. It actually received an IGMP membership report. So why is the outgoing interface null?
The network is an incoming interface.
PIM is not configured on the interface. Okay. Okay, yeah, just a break. So PIM is configured on the interface, and IGMP is configured on the interface. But good point. And now, next troubleshooting ticket, I'm actually emphasizing on that also. But all right, good. All right. Actually, you get a bag of chocolates. You get a. Oh, actually, that's true. So I don't have any more bags of chocolates. But yeah, that's true. That's true. You can get half. Okay, so anyways, what we do is that next command actually shows us what's the issue. We do show IP PIM interface, and actually what we see is that who is .19 here? Oh no, he's not the DR. This guy's .18. Who is .19? We go on .19, and we see, we have actually another last hop router. We changed IP addresses. This guy was changed to 18. This guy's some old router which had .19 preemptive, became the DR, and he built the multicast stream down. All right? So I've seen tickets where troubleshooting is like an hour, 2 hours, 3 hours, and we're on the router which is not a DR. And we jump on the DR and we see everything's perfect. Right? So make sure you know who the DR is on the segment. It's so important. Those roles are really important.
So that ticket was based on observations of the route and not receiving multicast traffic?
Exactly. We have tickets which come, we have tickets where we're saying, we don't have the correct state on this router. What is going on? And now, if you wake up at 2 o'clock in the morning or whenever, and you may not have reachability towards the server team or the guys, the receivers, right? You don't know if you're receiving traffic. You just look at that router and you're saying, I don't have the correct state. I'm surely not receiving traffic, right? So I'm emphasizing on that. Okay, troubleshooting ticket 2. Problem description is poor picture quality. Don't we love this? This is beautiful. Okay, so iOS actually bolds where the issue is. Isn't that great? That's a new feature coming out. I'm actually joking. That's not a new feature coming out. But actually, we have here registering. I've actually bolded that out. But what's important here? We have star comma G, what you need to do, right? We have star comma G on the last hop router. Incoming interface looks good. Outgoing interface looks good. S comma G, incoming interface looks good. Outgoing interface. Also on the rendezvous point. Right? Now, can anyone answer me this question? Why is the incoming interface here? Why is the neighbor all zeros? Because he's? He is the RP. So what's his interface towards himself? Doesn't have one. What's his neighbor towards him? He doesn't have one, right? So you don't want to emphasize on troubleshooting this. This is expected. Okay, we go down to the first hop router. We see the following state here. Can anyone point out do they see any issues here? Beautiful. Outgoing interface. Incoming is null. Outgoing is, well, yeah, we're emphasizing on incoming interface list here. What about, okay, is this expected? Yeah, but he's directly connected towards the source. So what's his PIM neighbor, what's his RPF neighbor going to be if he's directly connected towards the source? He doesn't have one. The source doesn't need to have PIM enabled, right? It just sends. Yeah. Okay, registering. Has anyone heard of stuck in registering? Okay, that's good. That's really good. Okay, so who is RP? We answered all these questions. We actually do show IP PIM neighbors, and we see it's empty. PIM wasn't enabled on the core interface here. But wasn't it funny that we actually had S, G here, we had S, G here also. Okay. So we configure PIM on the core interface, and we see everything starts working fine. Picture quality is great. Now to understand. Sorry? No, there is some picture quality. It's like fluctuating, or you know when you go turn a channel and it's like, oh, it's blipping up. It's like, oh, it's there, it's not there, it's there, it's not there. So that's pretty much the case. Okay, so now let's understand how the register mechanism really works, and when do we send a register stop. So rendezvous point, we're looking at this scenario. Rendezvous point here receives a star comma G from the network. The source starts sending. We encapsulate these packets into unicast towards the rendezvous point. Rendezvous point doesn't send a register stop. He joins the source. He joins the source. Very important. Now, in our case, what was happening is that this router was the first hop router before, which didn't have PIM here. So it meant that the rendezvous point could not join the first hop router, meaning that we were still sending these packets out, right? What happens usually if you don't have misconfiguration is that A is going to send the packets towards B now, right? B sends it towards C, and C says now, okay, I'm receiving native multicast packets on my S, G interface, my incoming interface list. I'm receiving it natively now. Now I tell the first hop router, don't send me those unicast encapsulated packets, right? Now, why poor picture quality? Well, if you have quite a lot of sources there, and all of them are going to be encapsulated into unicast and sent to the rendezvous point, that may cause high CPU. Now, it depends on the platform, right? If you have some low-end platforms, that may be the case. If you're running XR, ASR 9K, it's not going to be the case, right? But make sure that you don't have misconfiguration, right? But registering, stuck in registering, that's pretty much the case here. So we're always stuck.
So the reason why it's poor quality is because the packets were coming over the register, through the register.
Exactly. Exactly. And a lot of them were coming in. Okay, this is what we saw in the ASM, pretty much how we build the tree. So we have no receivers on the rendezvous point. We register that source. And since the C doesn't have any, anyone listening, he just sends, hey, register stop. Don't worry about sending those multicast encapsulated into unicast packets. What can cause stuck in registering? We have quite a few issues, right? PIM not enabled on all interfaces, TTL too low, right? If you're receiving a TTL of 1 here, you drop it, you're not going to register the source. M2U, if the source is sending 2,000 bytes with DF bit and your core interface is 1,500, you can't really encap that into the core, right? So you're going to drop that. And there are other issues also. So this is a good command, show IP traffic, and we actually see registers, how much we've sent, how much we've received. You're not going to receive because you're not a rendezvous point, but we sent 100. And register stops, example, we received none. So we're still not receiving a register stop. So it may also confirm the issue. Okay. Any questions? All good? Man, I don't have any chocolate either, man. We're both in pain here. Okay, so we run show IP mroute on 239 on the last hop router, the rendezvous point, and the first hop router. So if you don't know where the issue is, let's say you wake up 2 o'clock in the morning and you don't know where the issue is, if you go on those 3 checkpoints, it may hint you where the issue is, right? We check, so if you wake up and you go, oh, it's a first hop router, and you troubleshoot the first hop router, but you never did show IP mroute on the last hop router, then that would pretty much give you where the issue is. So we see that we don't have mroute state at all created on the last hop router. No mroute state created. So we should have a receiver directly connected. We check IGMP. It was already discussed, right? Okay. We check IGMP, and we don't have any IGMP state there. So a lot of smart people in the room. We have to check IGMP. We have to check PIM. Is it enabled on the interface towards the receiver? Right? We check this. And we check it with, sorry? Version 2. In this case, it's version 2, yeah. If you have version 3, it's backward compatible with version 2. But this is ASM, so we're leveraging IGMP version 2. Now, with this command, we actually see, okay, IGMP is enabled on the interface. Multicast routing is enabled. So PIM is enabled, IGMP is enabled. Okay, so are we sure we're receiving that IGMP membership report? You call up those server guys, right, and you tell them, I'm not receiving this IGMP membership report. Go ahead and troubleshoot your end of the network. Because we don't have state, right? If we don't have state, well, I'm not receiving an IGMP membership report. So they get back to us and they say, oh, we're sending it out. Your router is not working, right? Your router is doing something. Check your router, right? So we say, okay, let's do debug. Let's debug the group. We debug IP IGMP 239.1.1.1. We don't see anything being punted to CPU. Now you can check ACLs and all of that. We don't have that here. Debug IP IGMP 239. We actually don't see that membership report being punted to CPU. I get back to the team, the server guys, and say, all right, I've done debugging. It was a maintenance window of 1 hour, right? Get your stuff sorted and check the receivers. They come back to me and saying again, oh, no, you're the problem. So what we say is that, okay, let's do packet capture. Let's do packet capture on that interface where the receiver is. That's going to be black and white, right? If I'm receiving it, well, I'm at fault. But I know I'm not receiving it, right? Because it's always the receiver guys which are having issues or the sources. So we do packet capture, and funny enough, we actually have IGMP membership reports. There are a few things to check before you say, oh, it's the router, right? We check checksum, check MAC addresses, check the packet, make sure it's a valid packet. If that receiver is sending an invalid IGMP membership report, well, the router is going to drop it. And this is TAC on the call, right? Pretty stressed out, been pushing the ball for quite a while, but still playing it cool on the WebEx, right? Playing it cool, and why not check running configuration while we're waiting to think about what we should do, right? We check running configuration, and we see IP options drop. We see the drop keyword, so that's not good, right? So we investigate this. And we check, okay, IP options drop actually drops all IP packets, all IP headers which have the router or options field set there, and we do have an options field, hence we're dropping those IGMP membership reports. So this is a packet capture with IGMP packet here, and we have the options field set. And how can we troubleshoot this? Show IP traffic, and we see options denied. Now, the point of this ticket is you're certainly not going to have this configuration here, right? The point is that how do you troubleshoot such scenarios, right? We don't have mroute state. We check IGMP state. We don't have IGMP state. We do debugging or some kind of packet capture. Packet capture is perfect. We do packet capture, and we see black and white. If that's a valid IGMP membership report, Cisco, whatever vendor it is, they have to investigate that. So that brings up no passing the ball to anyone. That's how it is. Troubleshooting ticket 4. So here we don't have the first hop router. We're assuming that everything's fine on the first hop router. We have star G state here. We have incoming interface. This looks fine. However, on transit routers towards the rendezvous point, and the rendezvous point doesn't have this also. This is so it's a new setup. The customer wants to run multicast, and they're having trouble with actually pulling the stream down towards the rendezvous point. So we see a discrepancy here, right? We see A and B don't have state. Last hop router has state. So we investigate this portion of the network. What do we check, right? We check, do we have RP mapping? Do we have PIM neighbors? So we have both. Now, what's the next question? How do we get to the rendezvous point? We do show IP route, right? IP route gives us nothing. Now, do show IP Ceph, because it may be a default route. In the case it is, it's a default route, so we actually have an X hop. And it's going towards 20. But this A is 19 and B is 18. So where is dot 20? We need to investigate this, right? So where do we send the, So we have a discussion with the customer or the engineer, and they say, oh, we're actually running HSRP. So this is an interesting case, right? We actually have HSRP between A and B. We're routing towards HSRP VIP. So where do we send that PIM join to? 20, yeah. But in this case, you're actually looking at the RPF check. So how do you route to that source? That's how you know what's going to be in that. Remember that upstream neighbor field? You send the destination of multicast, but you say, okay, that PIM is supposed to be destined to 20. He's not 20. He's not 20. Oh, this guy's 20 because he's virtual IP, but he's not going to anticipate. He's not going to actually work with it because we actually don't have PIM neighbors. Remember, it's okay to have, we need to have an interface and an RPF neighbor. We need to have that PIM neighbor. But we don't have a PIM neighbor towards the HSRP VIP. Sir?
That's the virtual interface.
Yep, that's exactly right. So, solution is HSRP aware PIM. What this does, it actually on router A, so let's say router A is HSRP active. HSRP active will now generate PIM hello messages, sourcing it from .20, sends it towards the last hop router and towards B, and now we have a PIM neighborship. Now, what about redundancy here? If we always send to .20, and let's, in our case, .20 is this guy, the virtual IP address, is here, we always send towards here. If there's a failover, B doesn't have any state. It doesn't have any state because we never sent to B anything, any S, G or star, G state. We always sent it towards A, right? Is that clear?
Yes.
So if there is a failover, B becomes active, and B actually regenerates a gen ID field in those PIM hellos, and that tells last hop router, hey, there's actually a new PIM neighbor there, and now last hop router is going to generate all those S, G and star, Gs again when this guy goes down, and then he now has all the state. Yeah, you can check documentation, HSRP aware PIM. It's not supported on iOS XR, though. On iOS it's supported. Okay. Troubleshooting ticket 5. Okay, good. We don't have state on the first hop router. That's good news, right? We know where to troubleshoot, so we go to the first hop router. Okay. Now, we actually see and we don't have RP mapping. Now, there is something interesting here, is that if you don't have mapping, RP mapping on the first hop router, right? If you don't have RP mapping, sometimes you won't create S, G state, depending on the version you're running. Sometimes you will, sometimes you won't, right? Rule of thumb here is that you always have to have an RP for an ASM group. If you don't have it, even if you create S, G entry, well, you don't know where to send those registers, right? So it's not going to work. If you have it configured, if you have it configured, it's not a problem, right? So there you go. So it may vary between releases. And so make sure the first hop router has RP mapping. We configure the RP there, and we actually have S, G and star, G state now, and we know where to send those registers. Now, awesome. We're just about to close the WebEx, and the customer says, okay, multicast is still not working. Please investigate this, right? We don't know what's going on. We're not receiving multicast. So what do we have to do there? We check state on all those routers and make sure that that state is okay with mroute, right? Do you have a valid incoming interface list? Do you have a valid outgoing interface list? When we know that, then the hard part comes, right? We need to go hop by hop on every router and try to figure out where is that multicast traffic being dropped, right? That's how it is with multicast, right? So we go on the first hop router and we check, okay, show IP MFIB count. We're receiving 200 packets from the source. That looks good. We go to DR, so it's pretty much a rendezvous point joining the first hop router. So he is going to be in his outgoing interface list, so we should be receiving multicast packets here. We do show IP MFIB for 239.1.1.1, and we see here 299 packets. Okay, so the time it took for me to run the command here and here, 99 packets increase. It's a slow stream. Okay, we go to D. D is the outgoing interface list for, we go to E. D is the outgoing, E is the outgoing interface list for D, right? And we see show IP PIM interface count. I just ran 3 commands here which you could leverage. On this interface here, we're not receiving any multicast packets at all. So that's how we can figure out where that multicast stream is actually being dropped. So now it's a case, is D actually sending those packets out? I don't know. Maybe D is sending those packets and he is receiving this, but is he interpreting these packets? I don't know, right? We have to figure that out. So how do we figure this out? You have to check a few things, check MTU, right, packet capture. But there is a command which, it's a command which is dear to my heart, this command. I run show IP traffic and I see 298 bad hop counts. If this matches the flow of your stream, so if you're sending, I don't know, 300 packets per minute, you're not going to, but well, if you are, and it matches pretty much here, that kind of gives you a hint that it's actually this counter which is telling you what's going on with those packets. How do you confirm this? Well, you confirm it with packet capture. That's black and white. We do packet capture, and we actually see here the TTL was 3 from the source, time to live is 1, he's receiving this and he's dropping this. Expected. So what we want to get out of this troubleshooting ticket is that if you're sending multicast traffic, always put the TTL of 255. Really important. VLC, some versions have a TTL value of 1 when you're sending out multicast traffic. That may be an issue. But don't put it as 5 or 6. So let's say you know that there's going to be 5 hops between the source and the receiver. So you put 6, right? But what if there's a convergence event? What if OSPF goes down in an interface and then use a longer path to get to the receiver? That's an issue, right? So 255, always have the TTL value of 255. Troubleshooting ticket 6. So we have last hop router doesn't have S, G, right? We have star, G. This hints us on an issue, right? Outgoing interface list null, outgoing interface list null. First hop router has S, G and star, G. So why would this be the case here? Why would we not have an outgoing interface list on the rendezvous point for star, G? We didn't receive a star, G join, right? Should populate this outgoing interface list. So we think the issue is somewhere around here. And it's really important when you're troubleshooting, you grab those 3 commands and then I put them in Notepad and then I take a few minutes and just look at the output. It's really important. Just take a few minutes, look at the output, and then you can see discrepancies. Okay, so now we want to check how do we get to the rendezvous point. Maybe he's routing correctly to the rendezvous point. Maybe he doesn't know how to get to the rendezvous point. That's why we didn't populate the outgoing interface list. So we do show IP route. Let's look at the bottom output first. We do show IP route to the rendezvous point, and we see, okay, it's learned via OSPF, distance of 110. Our next hop is 011. Now we check the RPF database, and we see, actually, it's choosing a default route via static. So why do we have a discrepancy between RPF database and unicast rib? Remember, we said that RPF check usually leverages the unicast routing table, right? If you have a perfect network and you don't have static M routes or all that stuff, it's always going to leverage the unicast routing table, and that's perfect, right? But it's not always the case. So why do we have a discrepancy between RPF database and unicast rib? Well, a matter of fact, the RPF database pulls information from a few sources. It pulls it from static mroute state. It pulls it from DV MRP routing protocol. It's quite old, right? MPBGP subaddress family of 2, which is IP for multicast. And we have unicast routing table. So we check who is the best route from all those sources, and we push it, or RPF database picks between those sources. And by default, we actually use the lowest distance. Whoever has the lowest distance, we use the lowest distance. Now, if you're comparing this with unicast routing, it's not going to be the case, right? If you have a /32 over a /0 default, you're always going to use a /32. It's a longer match. That's how routing works, right? But in this case, it's a bit different. So we check configuration, actually, and we have a static mroute entry saying default everything to .9, and its distance is going to be 0, right? So without the IP multicast longest match command, we do a distance preferred lookup. We always check the distance between those entries. Doesn't matter what the longest match is. Doesn't matter how long it is. We check distance. 0 is better. With IP multicast longest match, we do longest match lookup across tables. Do you have any questions on any of the slides? Any questions whatsoever? It's the end of the day, I see. All right, so guys, some mandatory slides here. Continue your education. We have really good presentations on a lot of good topics, hot topics, right? So go ahead and have a look at them. Meet the expert. I'll be there pretty much tomorrow from 5:30 to 7:30. If you have any questions related to anything, could be XR, iOS, segment routing, EVPN, I'm really interested in that stuff, so we can have a talk. Fill in those surveys. It's really important to us, so we pretty much have valid feedback from you guys, and we understand what to make better next year. If you enjoyed the session or you didn't, right? Fill in the feedback. Really appreciate it. Thank you, everyone, for your time today. I hope it was an interesting presentation.